Alright guys, so I'm going to go through the dynamics mini quiz with you real quick. We're just going to go through each of the questions as quick as we can, just so you have an idea of what the answers should be and what the work should look like. Alright, so this is the first question. We have a force F acting on a block at angle theta with respect to a horizontal surface. The block is moving with constant velocity along the surface. So because it's constant velocity, we know that the forces are balanced. This is an important idea. Okay, anytime you see constant force, the constant velocity, you should say, okay, that means forces are balanced. Resistive force acts on the block. Which of the following correctly represents the forces acting on the block? So I recognize I've got the force pulling it up. I've got a resistive force going against that motion, right? The resistive force always goes against that motion. You've got gravity pulling down on it. You've got this surface pushing up on it, right? Which is your normal force. Now, I put all those together. Really, it comes down to, well, this one doesn't make any sense for friction to be in the same direction, which means it's got to be one of these three. We know that the force is acting up at an angle, so it can't be that one. So I'm down to these two. Oh my goodness, they look almost exactly the same, but they're not. What's different? When you see two things that look almost exactly the same, don't assume that either one's okay, because there's two that one of them is going to be slightly different for a reason. And when we look very closely at this, we notice that this one has a small reaction force, that one has a large reaction force. You'll notice that here the reaction force, or the normal force, is exactly equal to the weight. Now, sometimes that's okay, but that is not true. Newton's third law does not say that the reaction force is equal to the weight. Newton's third law says that if Earth pulls down an object and that object pulls up on the Earth, that has nothing to do with the normal force. Okay? What we do have to do is that our horizontal and vertical pieces have to balance each other, right? And so if my reaction force was equal to the weight, if this normal force was equal to the weight, then what about the vertical part of this force? Remember, that force is going up at an angle. If these two are equal, that means I have a net upward force, and therefore it's not going to have a constant velocity. It's going to accelerate upwards. So what we need is this force to be smaller so that the sum of those two vertical components is equal to the weight. Therefore, the answer should be letter D. All right, moving on to question number 2. Question number 2 asks us about a pendulum swinging between X and Y. The important thing to recognize is that it's asking about equilibrium. Well, again, what does equilibrium mean? Equilibrium means that the forces are balanced. If the forces are balanced, then that means that there is no acceleration. That means the velocity is not changing. Okay, well, is that the case? Well, what does it mean if the velocity is not changing? Does it just mean that the speed's not changing? No, it doesn't, because velocity is a vector. And how is that different from speed? Well, remember, vector has magnitude, which would be your speed. It also has direction. Is the direction of this pendulum swinging back and forth, ever a constant direction, meaning it's going in a straight line? No. Everywhere along this path, it is always curving. If it's always curving, then it's always changing its velocity. It's not changing its speed. Well, of course, it is doing that as well. But no matter where it is, it's changing its direction. If it's changing direction, it's got to be accelerating. Okay? You got questions about that? Come and see me. Next question. An object falls vertically from rest. Air resistance acts on the object as it reaches a terminal speed. Which of the following is the distance-time graph for the object? Well, we can get some definite answers right out of this right away. Recognize, number 1, if it's being launched, if it falls vertically from west, what is my initial velocity? The initial velocity, that's u, should be equal to 0. That's my velocity, right? What happens to the velocity as time progresses? Well, it's going down, it's going faster and faster and faster and faster. Velocity increases until we get to a point where it reaches terminal velocity. At terminal velocity, the velocity is constant. Now, we've done a lot of talking about velocity. That's what all this tells us about, is velocity. But that isn't what the graph is. The graph is position. So how do I get position or displacement from, how do I get velocity on that position or displacement versus time graph? Well, it's the slope, right? So what is this telling me? It's telling me that my slope starts as a slope of 0. What's the slope of 0? Horizontal. It then says the slope must increase. So I've got to have a graph where my slope is increasing. Then it says at terminal velocity, the slope is constant. So I've got a 0 slope, the slope increases, and then the slope is constant. The only one of these where all three of those things happen is this one, right here, letter A. That's the only one where it starts horizontally, the slope increases until we get to a specific point after which the slope is constant. Okay, still going up, but constant. Okay, that is the answer to that question. Moving on. We now have an object of 5 kilograms, suspended vertically by 2 strings as shown. The strings are of the same length, and the angle between them is 60. This is a Newton's second law question, okay? First thing it asks us to do is draw a Freebody diagram. Here is my object. I'm going to do it separate. I'm not doing it over here because there's too many lines. It's going to get way too confusing. I've got one tension pulling up this way, and I've got a second tension pulling up that way. T1, T2, doesn't matter. They're going to be the same because they're the same length. Angles all the same. And then, of course, I have the force of gravity. Now, why did I draw that one longer? Because I know it's at rest. And if it's at rest, then these two vertical pieces are going to have to balance that. Now, the next thing that I want to do is I want to write out my equations. I need to write out the sum of the forces in the x direction, and I need to write out the sum of the forces in the y direction. Don't put them all together. You put them all together, you're going to get it wrong. You've got to balance the vertical forces. You've got to balance the horizontal forces. So I'm going to go through each one of these forces one by one, and we're going to put those together. So force of gravity. What direction? Completely vertical. So I'm going to put in the negative force of gravity because it's down. And so the force of gravity is negative 5.0 times 9.81. So that right there is the force of gravity. All right, negative force of gravity. It's pulling downwards. Next up, we've got the two tensions, okay? Now, those are at an angle. Because those are at an angle, we want to break it into horizontal and vertical. Horizontal and vertical. Now, look, notice that both of those two triangles are exactly the same. They got the same angle. What is this angle right here? Well, this was 60 degrees, which means if I cut it in half, that's 30. It's a right angle, therefore this is 60 degrees, okay? That means that the opposite side, the vertical side, will be whatever that tension is. So tension times sine of 60, because that's the opposite side, opposite over hypotenuse. Okay, remember this is coming from tension equals the opposite side, the vertical tension. That is sine of 60. Sine equals opposite over hypotenuse, which is the total tension. I multiply by tension, I get T sine 60 equals Ty. If you're having a hard time with that part of it, come talk to me. Let me help you out. All right, so Ty. Okay, that is my vertical tension, which is going upwards. So I got plus T sine of 60. Okay, so that was just a label. Okay, then I've got the other tension, which is the same value of T, and it's still going up. So that's going to be plus another T sine of 60. Okay, horizontally, I'm going to have T cosine of 60 because this one's going to the right, and it is the horizontal part. That's the adjacent over hypotenuse. And then this one's going to the left, so that would be minus T cosine of 60 because this one is pulling to the left. Now, because it's at rest, that means all the accelerations have to be equal to 0. The sum of the forces must be 0. So at this point, I can change this to 0. 0 equals that, which of course that minus itself equals 0. It also could then support this fact that we're saying that these two tensions are equal. Yes, they have to be equal, otherwise you wouldn't get a 0 here. Once you have that, we then put in a 0 here, acceleration. You should then be able to put this into your calculator and solve for T. Okay? I I'm not going to answer it right now because I believe that you can solve that, all right? And I'm going to go on to the next question, okay? Last question. An object of mass 4 kilograms slides from rest without friction. Note that it says without friction. Don't put friction in your sign diagram. If there's friction, don't add a resistive force. Don't add any of those things if it says without friction. Down an inclined plane. Inclined plane. Okay, so inclined plane, object sliding down. Okay? The plane makes starts from rest, all right, which is important. It tells me that my initial velocity is 0. The plane makes an angle of 30 degrees. So 30 degrees. Notice that the first thing I'm doing, I'm drawing a picture with everything here. Some of you didn't even draw a picture. All right, so let's go ahead and draw a picture, 30 degrees with the horizontal, and the object starts from a vertical height of 0.5 meters. Okay, so 0.5 meters. With that, I should be able to find the lengths of the other sides. Do I need that right now? No, but I could find it, right? Using, this is a 30, 60, 90 triangle. So it should be pretty easy to get those other sides if necessary. Okay? Then find the net force on the object as it slides down the plane. So to find the net force, the first thing I'm going to do is I'm going to draw the forces that are on there. Okay? Well, I've got the force of gravity pulling down, or you can call it weight. Don't call it gravity. Force of gravity or weight. And then you've got the normal force of the ramp. Okay, again, I don't like just calling it normal force. I like to say, well, what in the heck is causing the normal force? Well, it's the ramp pushing on our block. Okay, any other forces? No, nothing else is touching it. There can't be any other forces. That's it. So those are our two forces. Now, I learned in my homework, because I did all of my homework and I watched all of Mr. Bywater's other videos, that when it's on a ramp, I should tilt it. Because when I tilt it, it's going to simplify things later. Okay, so I'm going to redraw this so that I've got the x-axis going this way and the y-axis going this way. Now, in a situation like this, it may not matter a whole lot, but in the long run, it will make things simpler, especially if we do add in friction or if we do add in other forces pulling on there. It will be easier if you tilt your axis, okay? So, I have a new axis, which is like this. It doesn't matter, vertical, horizontal don't affect each other, even if it's at an angle, okay, as long as it's the vertical and horizontal. So what I've got now is I've got the normal force, which is going straight up along my y-axis now. So this is force normal. And then I've got the force of gravity, which is, this is my y, that's my x, so it's between the negative y and the positive x. So my force of gravity, which is going down in this direction. Now, if you do that, then it's going to be a little bit easier for you to determine how to write these equations at this point. This should not be an overly difficult problem because there's only two forces there. We're neglecting friction. Okay? So it was straight down. It's been rotated over 30 degrees. So this is 30 degrees right here. Okay? We know the force of gravity because the force of gravity is equal to the mass times gravitational acceleration. So the overall force will be that 4 kilograms times 9.81. Please, please use 9.81. Don't use 10 unless it tells you to use 10. Okay? Gravity acceleration on the surface of the Earth is 9.81. Okay? All right, so we got that. We've got the force of gravity. Now, in order to be able to find the net force, well, we know that it's not accelerating in this direction. That's our vertical direction. Right? It's accelerating down the ramp, which is our x. This is why the whole tilting the axis thing is going to simplify, because now it's only accelerating in the x direction, which means it has a net force in the x direction. The vertical, up and down, it's not leaving the ramp and it's not sinking into the ramp. Therefore, the vertical forces have to balance. And so if those vertical forces balance, that means that the vertical part of gravity must be equal to the normal force. All right? So I can find those forces. I can find, as necessary, this is now the adjacent side to the 30. So that will be 4 times 9.81 times cosine of 30. And then the horizontal there will be 4 times 9.81 times sine of 30, because that's the opposite side. right? Sine is opposite, so peto. Okay, now at this point I'm going to write out my sum of the forces. I got some of the forces in the x direction, and I got some of the forces in the y direction. Okay, so x direction, well, I only see one force. It's that horizontal piece, it's now horizontal of the gravity. So that's 4 times 9.81 times sine of 30. Okay, in the y direction, I've got the normal force, which is upwards, and then I've got this one, which is downwards, so minus 4 times 9.81 times cosine of 30. Now, at this point, I know it's not accelerating up or down. I could make this 0. I could solve for the normal force. The normal force could be used to find friction if there was friction. Of course, it's not asking for that. Okay? We're saying there's no friction. Therefore, all I'm going to use is this one. Sum of the forces is equal to MA. And I know the mass is 4. That should allow me then to calculate a value for the acceleration. I'm not going to find that value. You find that value. Okay? Now, that acceleration, sorry, first A, just kidding. A was just the net force, which is just this number right here. These two have to balance, right? So that it doesn't leave the ramp, it doesn't sink into the ramp. Those two have to balance, so that's 0 vertical net force. The net force, therefore, is just whatever this horizontal piece is, and I can get that from my equations. Okay? Now, moving on to part B. Part B says determine the speed of the object when it reaches the bottom of the plane. So now we're talking about speed. Now this should start to make you think speed, velocity. Oh, now I've got something where I've got to be using kinematics. I should be thinking about my SUVA, my kinematics equations, right? So, therefore, I'm going to list down the information that I have. S, U, V, A, T. Okay? Well, I've got my initial velocity, which I wrote down earlier. Good thing I wrote that down. My initial velocity in this direction is 0. I can calculate my acceleration. I accidentally went a little bit further than I should have earlier. I can calculate acceleration using sum of the forces equals ma. I should be able to get that acceleration. Okay, so I'm going to put just a box around my a there, so this is going to be whatever that acceleration is when I solve for it right there. So you can solve for acceleration. Okay, what else can I get? This is what I want. I want the final velocity, right, the final speed as it gets down to the bottom of the plane. So I either need time or distance. Now remember at the beginning I said because we have this distance here, I should be able to use this angle to figure out how long that is. Well, this is a 30, 60, 90 triangle. You should be able to figure out using either trig or special triangles that this has a length of 1 meter. So I'll put down 1. Now I have S, U, and A, and I want V. Figure out which of the SUVOT equations. It should be the one that looks like this. V squared equals U squared plus 2AS. Please use that to solve for the velocity. All right? It doesn't have time. It's the only equation that doesn't have time. All right? That's it. See you tomorrow.